we'll have Dr. Li Gao, Staff Software Engineer, LinkedIn, to address how LinkedIn handles challenges of data infrastructure.
Good morning, everyone. My name is Li Gao. I'm from LinkedIn. I joined LinkedIn for about 4 years ago. Ever since then, I've been working on various systems in the backend data infrastructure side on LinkedIn. So in today's presentation, I'm going to talk about the LinkedIn's backend infrastructure, the evolution of LinkedIn's backend infrastructure, so that it, over time, is able to respond to the ever-growing need for scaling out. This is now. So in today's talk, I'm going to first briefly talk about LinkedIn and our mission statement. Then I'm going to talk at a high level about the 3 main products, and then the big data feedback loop that is powering and refining LinkedIn products. Then I'm going to focus on the data infrastructure part, and then talk about how the evolution of the different systems in the backend infrastructure, how we use that to continuously scale out LinkedIn at lower cost. As you may or may not know, LinkedIn is the world's largest professional network. I'm not sure how many of you here are LinkedIn members. Maybe we can do a show of hands for the people that are already a LinkedIn member. Well, looks like I have good turnout. So our mission at LinkedIn is be able to connect all the world's professionals and make them more productive at what they do and be successful at what they do. As of today, LinkedIn has 225 million members worldwide. And every second, there's more than 2 new members sign up to the site. Every month, we have 130 million unique visitors to the site. And in addition to the professional identities, we host 2.9 million company profiles so that for professionals, if they want to follow companies in terms of what they do, their business plans, you can do that too on LinkedIn. So at LinkedIn, we have 3 main categories of applications. They're categorized solely based on the kind of data that is powering the application. So the first example is the user profile data, which is on top of a large data set, and it accommodates update rate at the medium level and has very high read rate. And the freshness guarantee for the profile data is at level of less than a second. Why is that? Because when a user is updating their profile and hit the save button, it's very likely that she or he will expect that the update portion of the profile shows up in a refreshed page. Because of that, the freshness guarantee for the profile data should be at level of less than a second. So we call this kind of data online data. To the other extreme, we have application like People You May Know, which again sits on top of a huge data set. And it requires a very expensive computation to generate the result set, and it has very high read rate. However, the freshness guarantee for People You May Know is at level of hours, because it is usually the case where a member is going to take quite a bit of time, couple days or weeks, to add all the people that in the People You May Know list in its connection. So if a new member registered on site, it is okay for us to have that person's show up in someone's people you may know list. So that's why we say the freshness guarantee for people you may know data is at level of hours instead of seconds. So this is to the other extreme compared to the member profile data. And we call this offline data. So now we have the two extremes. We talk about the, what do we call the moving data set, the nearline data. Why is a moving data set? The nearline data we're referring to are like news, member feed activities like Twitter stream or Weibo stream, right? So for this kind of data, both the read and write rates are very high because you have a flow of information continuously come in, and you always observe, browsing. The member is always browsing those information, right? The freshness guarantee for this type of data is at the level of minutes, because it is perfectly okay for you to read a news, a few minutes after it come out. You don't need to, read a news like a very second it comes out, right? But it's also not good for you to read a news that's several hours late. So we call this a nearline data with a freshness guarantee of minutes. So those are the three categories of, LinkedIn application or data set that the application sits on top of. So here we have what we call the three-phase abstraction for LinkedIn, that the LinkedIn data infrastructure consists of. As you can see in this diagram, we have both online and nearline system directly interact with our applications. At the same time, both the nearline and online system talks to the offline system, so that we continuously send events into the offline for analytic processing, ETLs. And then as we have the results available from offline, we have to have a way to get them into the online serving platform so that the applications can access them. Right? So what do we mean by online? Again, we're referring to activities that should be reflected immediately, such as member profile updates, company profiles, and endorsements and skills. And the nearline data, we're referring to activities that should be reflected soon, like the user activity streams, profile standardization, news, recommendations, job you may be interested. And the offline data refers to the activity that can be reflected later, like the people you may know, connection strings, and some certain type of news, or your next best ideas. Right, so as I mentioned earlier, the LinkedIn's data infrastructure is part of this big data feedback loop that LinkedIn apps are solely powered by and refined by. So this big data feedback loop, as shown in this diagram, we have the member, once they're on site, they generate activities and perform updates that will be captured and stored in their data infrastructure, which then send signals to our scientist. The scientist will take this data, apply sophisticated data analytic model on top, and produce sort of recommendation to the product team in terms of what product has been working well, and what product has not. And this gives the feedback to the product team to keep refining the products. So the refinement of products leads to more engagement of the user. And there you can see the loop keep on going. As we have the more engagement, that means more member on sites generating more activities, which would require the data infrastructure to be able to continuously scale out in order to accommodate what we need. And then we are able to send stronger signals to our data scientists, and therefore they give better insights to the products. So in the rest of the presentation, I'm going to do a little deep dive into the the data infrastructure part. So I'm gonna tell you a little bit more about how LinkedIn's data infrastructure evolve for scaling out purposes to complete the big data feedback loop. Before I go into the detailed discussion, I have to warn you that because our data infrastructure consists of a lot of different systems, and I'm not able to go into a detailed discussion on any one of those, otherwise we'll be out of time. So you have specific questions, you can always catch me afterwards or send me emails. We can do some in-depth technical discussion. So again, as I mentioned, the three-phase ecosystem that the LinkedIn infrastructure has to face is sort of a diverse, complex, and they're specific to different applications. And for that, to solve some of the problems, we directly use the off-shelf solutions, such as Oracle, Teradata, MySQL, and Hadoop. But at the same time, we also have significant investment to our homegrown, deep, and interesting platforms, such as the distributed key value stores like Express or Voldemort, a high throughput, low latency messaging system like Databus and Kafka, and we also build our cluster management and workflow management like Helix and Azkaban. So as you can see, we have built a variety of systems in our backend infrastructure to facilitate the requirements of different applications. So now I'm going to go from the most simple sort of infrastructure that we have in the earlier days at LinkedIn, and then show you how it evolves into that complicated stacks. So as most of the other internet startups in the early days, when LinkedIn first started, we store everything in Oracle, right? Everything's RDBMS based. Our application read and write data directly into Oracle. What happens as we're introducing new features like faucet search, as we're building what we call the connection graphs for our members to be able to easily figure out their second-degree connections or third-degree connections? We realize that the RDBMS model can no longer provide what we need in terms of feature, in terms of the performance, and the scale, and the cost. So we built a data bus so that we can get the data out of Oracle and have the data to be able to upload into other data backends to perform what we do. So Databus is a timeline consistent change data capture. What it does is it streams out transactions out of Oracle and have the transactions to be applied into other data backends, such as search backends, graph database, and even for read-only replicas. Databus allows us to scale out read-only traffic from the original RDBMS system. Again, at high level, the Databus consists of 4 components. We have to your leftmost the database, where we have a capture process sitting there, which accumulate events as they're taking place inside the Oracle database, and it tracks them based on the SC and the system commit number. And then we have the relay set in the middle. It constantly pulls the data out of the capture and stage them on the relay, so that downstream consumers can suck the data out and apply them as needed. So there are 2 types of downstream consumers for Databus. One is the client library that is embedded in the applications. Another type is what we call the bootstrap database. It also keeps consuming the events from the relay and apply to a local database. What it does, the trick it does is that it keeps deduping for updates, for repeat updates on the same row. so that if we have a new service get brought up online, or if a specific service wants to consume the data from some time in the past, instead of going against all the way to the core database, the client can choose to bootstrap itself from the bootstrap database. Again, as you can see, this is our way of scaling out, helping scaling out from the core database by introducing the bootstrap database and allowing the consumers to be able to bootstrap from them. So Databus is sort of source agnostic, meaning that you can build a capture process for different data sources like Oracle, MySQL, etc. And it provides a transactional sort of semantics in terms of deliver the events. So for all events in RDBMS terms, all events that occurred in a transaction, they're delivered either at whole or none into the downstream consumer. And they're delivered in the order they're committed in the RDBMS system. And we have this at least once deliver guarantee, so that it will never miss an event, but you do have to handle duplicates sometimes when there's a failover happen. In LinkedIn, we're running tens of relays that are consuming data from hundreds of Oracle instances. And end-to-end latency, i.e. from the time the event took place in Oracle until the time this event gets delivered to a client, is less than a second. So we're providing this low latency sort of message delivering system through Databus. So now that with Databus, we're able to scale out read-only traffic. What about read-write traffic, right? For systems that requires just a simple key value access, we don't really need Oracle. This is when we build a system called Project Voldemort. Project Voldemort is sort of a system built based on the blueprint of Amazon's Dynamo system, which is a highly available and highly scalable key value store. With the introduction of Voldemort, we're able to offload the workload, a simple key value workload, off the Oracle system. And what Voldemort offers is a very low-cost way of scaling out your data access. So, little sort of technical discussion on Voldemort side here. Voldemort, there's three takeaways on this slide. Three unique features about Voldemort: the scalability, availability, and the layered design that gives you a flexibility. So Voldemort achieves scalability by using what we call the consistent hashing. So people have used consistent hashing, is familiar with this hash ring in the middle, where we partition the key space into multiple chunks, and then we map them onto servers. So initially, we over-partition the key space, map multiple partitions onto the individual instance of the cluster. Then as the workload increase, and we're reaching the capacity threshold of the cluster, we're able to quickly add new machines, add more commodity boxes, and then tell the system to rebalance. The rebalance process would move the partitions from some subset of partitions from existing nodes onto those new nodes, so that the workload is evenly distributed among the existing host as well as the new host. So that's how Voldemort achieves sort of scale out at a low cost. To the leftmost, Voldemort is sort of having a large number of storage nodes sits behind a router through which the clients access the database. We're using quorum-style replication to achieve sort of high availability, fault tolerance. And based on the quorum configuration, we're able to make trade-offs between consistency semantics and the sort of latency and availability, writes availability. And the third part is about the flexibility, right? Voldemort uses layered design as illustrated to the rightmost stack, software stack, where you're able to sort of deploy different layers on different locations. For example, we can deploy the routing layer co-located with the client. Then we have what we call the fat client deployment, where the routing is done on the client side. We can also deploy the routing on a separate instance. That's when we have the thin client going through a router. Depending on, it all depends on your specific requirement of your application. And on the bottom layer, we have sort of pluggable storage layer, where depending on your application need, we can swap in different storage engine implementation. Shall it be BDBJE, MySQL, or even read-only. So we can swap those in based on at the deployment time. So Voldemort is very widely used at LinkedIn. We're running about 14 clusters with a combine of 400 nodes. And at peak, we're handling 400K QPS. And we're hosting about more than 100 terabytes of data in combined on Voldemort alone, with a average latency of 2 to 3 milliseconds, which is quite good compared to the traditional RDBMS. That is why I was saying initially, why use RDBMS solutions, which are a lot more expensive to scale out, when your application don't really need it. Then it brings the question of, what about my application that requires more sophisticated data model? What if I need to do secondary index lookup? What if I need to do text-based search? This is when we introduce Espresso. Espresso is an index timeline consistent distributed data store that is used to power applications like email boxes, where secondary index lookup, text-based search are commonly required. So Espresso system has a very complex data model. It has this, what we call the hierarchical data model. As illustrated in this sort of diagram, we have a mailbox database with the 3 tables in it. The upper left table is what we call the metadata message table. It captures the type of messages a user has. And bottom left is the actual message table where the content of the message is stored. And to the right, we have the aggregated message table where we store sort of aggregate total counts of your messages and number of unread messages. So on each resource, meaning on each table, we're able to provide a richer functionality compared to the key value model, where we can perform conditional updates, partial updates, and we also implement atomic counters. And within a resource group, that means within a single instance of Espresso storage node, we're able to provide sort of so-called the transactional semantics. You're able to perform updates, queries within joins of all 3 tables. And we can do secondary index lookups, and as well as text-based search. Obviously, we use Lucene for indexing, which is not captured on this diagram, but will be kept as illustrated in this one, where this is a high-level sort of a diagram for Espresso system, where an application is accessing the storage nodes through a routing tier. On each storage node, we have a MySQL as a storage engine, and we also have a Lucene index. So the update events from the application will go through a router onto a storage node. And then update will take place first on the MySQL instance. And then through a data bus replication, that update gets propagated to the Lucene index, as well as to other storage node. So here's another difference for the technical guys, where on Espresso, we use what we call the master-slave replication style. As opposed in Voldemort, we use quorum-based replication. So if you have worked on in this area, you know the trade-offs between the master-slave versus the quorum-based replication, which I will not go into details here. And to the right, we have the cluster manager that is built on top of Zookeeper. We use that to keep the mapping information from a key to a partition and to a server, to a set of servers, a storage node, so that our client, by can pull the information out of the cluster manager before it access the data. And at the same time, the cluster manager is able to provide sort of automatic failover, automatic load rebalancing in case of skewness, or when the workload has gone up to the sort of capacity threshold. Then the cluster manager would notify our operation teams to say, hey, it's time for you to add new boxes, and I'm going to rebalance all the workload into those new boxes so that we don't sort of key over and die. So this cluster manager is actually not specific to Espresso. It is really a sort of a distributed state machine that you can use to implement configuration management, automatic load balancing, fault tolerance, and automatic rebalancing. And it's not only used in Espresso, but also used in other distributed systems at LinkedIn, such as Databus and Search Backend. Helix was open sourced last year, April last year. So as many of other LinkedIn's infrastructure systems, we like to open source it once they're made into production quality, so that we can share with the rest of the world, and we can also get help from people who are interested in helping us making the system better. Like Voldemort and Databus are all being open sourced for a few years. So far, we have talked about how we scale out our online and nearline system with Databus, Voldemort, and Espresso. What about our big data feedback loop, right? How do we get all this data into the offline system so that our data scientists can make use of this data, right? The challenge we're facing here is that we have all different services that wants to have their data sort of load into offline systems. That's what we call the ingress problem, right? How do we sort of aggregate all those events in a manageable fashion so that once we don't do ad hoc solutions for loading data into our offline data system for every single components we're running at LinkedIn. This is when we introduced the Kafka, which is a high-volume, low-latency messaging, POP-SOP messaging system, through which we're able to aggregate all events that are needed to be loaded into Hadoop into this one place. And then we build sort of our ingress adapters to write the data into our offline data system like a secured Hadoop or data warehouse. So this is a high-level overview of Kafka architecture. Again, Kafka is a very highly scalable system where producers can create messages for different topics. And then each topic is sort of like a message group that can be partitioned. In case that some topics, some message groups become popular, and then we want to be able to partition the workload and have the partitions deployed onto multiple instances. And as the message group gets more and more popular, we're able to continuously add more commodity boxes to help it continuously scale. And just recently, we have introduced in Kafka 08 a new feature in Kafka. It's what we call the inter-cluster replication. In order to make our messages more reliable, be able to survive single node failures, we introduced this mechanism for Kafka to be able to replicate its message onto multiple machines, so that when one node down, the other one can take over in terms of allowing message to be produced as well as allowing messages to be consumed. And we use Zookeeper as sort of a metadata management system, so that the consumer, when it's ready to consume messages from Kafka, it knows what partitions what instances to go to fetch the data from. Kafka is a very popular system at LinkedIn. Here just give you some statistic sort of feeling. We're doing like 10 billion writes into Kafka every day, and we're reading 50 billion messages out of Kafka each day. Here you might be wondering, how can you read more messages than you send in, right? So Kafka is kind of different than a traditional queuing system, where each message, after being consumed once, will be removed from system. Kafka allows events to be persist in the system up to its retention date. Before that, the same event can be consumed multiple times by different clients. So through Kafka, we're solving our ingress problem. What about egress, right? After the data is being loaded into Hadoop, after the analytic jobs have been running for a few hours, we have the results. How do we make the results useful, right? How do we because the application can't access those data unless they're made available in the online serving platforms. How can we make this happen is our next challenge. Here we use a combination of Web HDFS and Faust for our egress solution. There's two ways you can get the data out of Hadoop at LinkedIn. One way is by fetching an entire data set through Web HDFS. This is really mainly for initial data loading or for read-only data set refresh, daily, weekly, or monthly, where the data is computed in Hadoop and being bulk loaded out through Web HDFS. And for this kind of a data set, one requirement is that once it's uploaded, you cannot really modify it online. So what about the applications that have this requirement, where not only I wanted to get the data stream from offline system, but also I want to have it merged with my online updates. Our solution to that is to use a combination of Kafka and Faust. I will have a little bit detailed discussion on Faust, which is a streaming platform that understands the partitioning layout and replication of the online serving platforms, so that it can streams the update events into those online serving platform, and it can merge with online updates. So before I get into that, I will just show you a diagram on our offline, what we call the batch environment. What's going on inside our offline system. Right? If you just focus on this square in the center, at LinkedIn we mainly run map-reduced jobs on top of Hadoop, and all those jobs are created, controlled by our job controller. And the job controller also coordinates when we need to get the data, when the results are ready. Then through the job controller, it notifies the online serving system saying, now it's time for you to fetch, the data is ready. Right? So the workflow management system is called Azkaban. It is it gives you a GUI-based user front end where you can create your jobs, submit your jobs, and you can also, through this GUI front end, to monitor the progress of your job and be able to see the event logs to see what's going on, if something happens in your job. And then for creation of our sort of read-only data set, basically for each map-reduced jobs, it generates read-only data file in the following format, illustrated to your right. We build index files that allows, based on the key value access pattern, allows the mapping from index file into the data file segment. So all those index files and data files are generated in Hadoop, and then through Web HDFS, where the online serving platform can fetch those data out in parallel, because online serving platforms are usually a distributed system where all the different nodes wants to fetch different segments of the data at the same time. And our Hadoop system is sort of secured so that whenever a fetch is initiated, we need to go through authentication process before we allow the fetch. Otherwise, we're in the danger of leaking the data through Web HDFS. So for the data that requires on the merge between the offline and online updates, our MapReduce jobs will generate those data in Avro format. And in each Avro records, we annotate what fields should be used for key and what are the value fields. And those records, once generated in Hadoop, it'll be sort of published into Kafka. And then we run a file system that is illustrated to the right. We run the file system to consume events from Kafka and then stream them into the destination data platform. So here, Faust is what we call a pluggable streaming system that allows plugins to be written so that we can consume from different data sources such as Hadoop, Teradata, or any other data sources. At the same time, you can write plugins for destination data sources like Voldemort Expresso and many other online serving platforms for data serving. And the beauty of Faust is that while all the plugins are sort of source and destination agnostic, dependent, we have common set of functionalities built in Faust, such as monitoring, throttling, and scheduling. So if any of you have experience in operating a large-scale system, you will know that monitoring is very important, because if you have no insights into monitoring, you will have no idea what's going on in your system. And sometimes throttling becomes very important if you have multiple batch jobs trying to load the data onto your online serving system, but your online serving system can't handle the load. This is where the throttling becomes important. And also scheduling allows you to optimize sort of your resource, your network resource. Be able to schedule all the sort of upload events at a different times so that you don't end up having bursty traffic at one time period and then leaving your network idle in another period. So monitoring, throttling, scheduling are important. That's why we built all this inside the Faust, allowing plugins to be built for source and destination streaming. So in summary, this big data feedback loop at LinkedIn is very essential for our product, for the product to evolve, to be better refined for serving the better of our member. And as a result, the infrastructure that's part of the big data feedback loop needs to continuously innovate and iterate over and over for scale-out purposes. And the fast-moving, big, and clean data plus agile metadata is the key. And the data-driven products, as I mentioned earlier, needs agile feedback infrastructure and the measurement methodology in order for our developer and the product owner to know what works and what should be improved, right? And the data-driven experiment is very important because it allows insight and to the product so that we can refine the product quickly. And the last thing I want to call out here is the recommendation-driven product is the future, at least for LinkedIn. Because we know the professional identity, a background of our member. So based on that, our analytics can tell our member, for example, the people that you may need to connect, the jobs that you may be interested, right? The news that are relevant to you. So those recommendation-driven products, based on the result of offline analytics, is sort of the future of where we want to drive our product to. And before I conclude the talk, I just wanted to call out that, LinkedIn is continuously refining its offline data infrastructure, and we like to get help whenever we can. In addition to the all the systems that I've covered, we're continuously building, sort of recommendation and optimization, solving those recommendation optimization problems for our data analytics and the data mining. And we're building our next generation ad hoc OLAP queries on top of Hadoop. This is where we like to get help with. And we're also building sort of the graph computation integration loop from that combines the offline mining versus online access. And we're also building the what we call the near real-time data streams inside our nearline infrastructure. And we will have a Q&A session later this afternoon, so I won't take questions at the end of this talk. But you can always feel free to send your questions to me at algal@linkedin.com, or you can ask me later this afternoon during the Q&A session. Thank you.
Thank you, Dr. Li Gao.